We saw in our last section how the sum and difference identities are helpful in evaluation as well as simplifying trigonometric equations. In this section, we're just going to add some more of these identities to our bag of tricks as we move into solving trigonometric equations in the final section of the chapter. The first set of identities we're going to look at are what are called the double angle identities. Here's the list of the double angle identities. Notice all that's happening is we are doubling whatever angle it is that we're looking at to take the sine of or the cosine of. So let's prove just one of these. We're going to take and prove the cosine of 2u. Well, we know that the cosine of 2u is equivalent to the cosine of u plus u, and we just looked at our sum identities. So we know that this becomes the cosine of u times the cosine of u minus the sine of u times the sine of u. That reduces to the cosine squared of u minus the sine squared of u. But notice here that this we can rewrite also in terms of cosine. And so we get cosine squared of u minus 1 minus the cosine squared of u. And again, that comes from sine squared plus cosine squared equals 1. And then that we can reduce to cosine squared of u minus 1. And when we distribute plus cosine squared of u, which gives us 2 cosine squared of u minus 1, which matches here. So we can see all these different values or ways to represent the cosine of 2u. So what do we use these for? Well, let's do an example. Suppose we know that the cosine of x is -2 over the square root of 5. Since cosine is negative, and we know that the sine is positive, we know it has to lie in the second quadrant. So we can draw a picture here and show our reference angle x here. We know that we're going to have the cosine is -2 over the square root of 5. And so using the Pythagorean theorem, we know that this leaves us with a side here of 1. From that information, then, we can determine the sine using our relationship that sine is opposite over hypotenuse, which gives us the sine is 1 over the square root of 5. Note, we could have also done sine squared of x plus cosine squared of x equals 1, which would have resulted in the sine squared of x equaling 1 minus the cosine squared of x, and then plugging this in, and then taking the square root, we also end up with the same value of 1 over the square root of 5 for the sine of x. Using the formulas or the identities that we just showed, we can then calculate the cosine of the double angle of 2x is cosine squared of x minus sine squared of x, which our cosine squared of x is going to be 4 over 5 minus 1 over 5 for sine squared of x, which becomes 3 over 5 for the cosine of 2x. For the sine of 2x, using our double angle formulas, we know that that's equivalent to the sine 2 times the sine of x times the cosine of x, which is 2 times 1 over the square root of 5 times -2 over the square root of 5, which is -4 over 5. And last but not least, we can use the double angle identity for tangent. We know that this is equivalent to the sine of 2x over the cosine of 2x, because we know sine over cosine, and we've already calculated both of those, which gives us -4/5 over 3/5, which results in -4/3, or we can use the idea of that tangent of 2x is equal to 2 times the tangent of x over 1 minus the tangent squared of x. And using our triangle here to figure out the tangent, we know that tangent is opposite over adjacent. So we get 2 times negative 1/2 over 1 minus 1/4 when we square 1/2, which ends up as negative 1 over 3/4. And when we do that complex fraction, we end up with negative 4/3, which is the same. We can also use this double angle identity idea to prove other identities. So for example, here, the sine of 3x, notice that the sine of 3x can be rewritten as the sine of 2x plus x. And then using our properties and identities from the previous sections, we know that this becomes the sine of 2x times the cosine of x plus the cosine of 2x times the sine of x. And then using the identities that we have just learned, we can apply the double angle identities, which gives us 2 sine of x cosine of x, and then still times the cosine of x, plus 1 minus 2 sine squared of x sine of x. As we simplify, we get 2 sine x cosine squared x plus sine of x minus 2 sine cube of x. And then we can do some reducing and simplifying here by plugging in our Pythagorean identity. This becomes 1 minus sine squared of x, that's from the cosine squared of x, plus sine of x minus 2 sine cube of x. And then when we multiply out, we get 2 sine of x minus 2 sine cube of x plus sine of x minus 2 sine cube of x, which then results in that equivalent that we were trying to prove.